All right, so let's start again.
Okay. Uh-huh. Okay. 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 Let me look how I can solve that.
All right, so
Okay, before you
let
back.
me restart this. Okay, so this note was given,
Okay.
this notebook was given to every one
Okay.
of you. I'm pretty sure by now you all have it. So basically, it's just it gives us fundamentals of PyTorch and how we can use it to build complex models, complex machine learning models. All right, so in the last our last meeting, we had um, gone through this note up until some point. So for some of you, I believe that you would have also tried to run the cells in the notebook. All right, so if you're running this locally, like if you've installed maybe Anaconda or Miniconda, you'll be able to run this locally on your machine. However, for some of you that don't have, or so some of you that have the Intel Evo laptop with the Core i7 and a non-NVIDIA GPU like mine, you may have to add this code. Okay. Essentially, what I'm just trying to say to it is it should ignore all the KMP duplicates library that will pop up. So if you do this, you should be able to run all the cells within this notebook. Now in the next cell, if you recall in the last meeting, I said that to import the PyTorch library, simply just import touch, that's all. And then you can also check the version of the library that you have currently running in your machine. So in my own case, I have version 2.1.0, but as at the time of making this note, it was 1.10.0. Also, we introduced the concept of tensors, dimensions of tensors, and the shape of tensors. So if you recall, we said the dimension, think of it as counting the number of open bracket from the left. In this case, this is a tensor of 3 dimensions, okay? But the shape of this tensor would be the number of elements in each dimension, okay? All right, so this is, and we also discussed that you can, tensors, basically, you can use it to represent a lot of stuff. Like in this case, this is the tensor that represents 2 by 2. So this is the first channel with 224 by 224. Second channel also 224 by 224, and the third channel also 224 by 224. Okay. Now I want you to try to not visualize this as some cube, because we will, in machine learning, most especially, you'll be working with very high dimensional tensors. So you should just think of it as having certain number of dimensions, and each dimensions have shape. That way it's easier for you to work with, and you don't struggle trying to visualize it in your head, because once you go past 3 dimensions, then the visualization in your head becomes difficult. Okay, so to create a tensor, it's actually very simple. It could be a scalar, in which case it's just a number. Like in this case, we create a tensor of values 7. And of course, if you recall in our class, this is not a list of numbers, it's just a scalar value. So there are no, this very tensor has no dimension. As a matter of fact, the dimension is 0. So if you check the value here, you see that this dimension is 0. Okay. You can also retrieve the value of a tensor using the function or the method within the tensor class called item. So scalar.item will give you the value of that tensor. We also said that you can have an array tensor. Okay, so to do that, you pass a list of numbers. Okay, this creates an array. Now, it's important because in the case of a tensor, the data type must all be the same. It's actually an array represented in memory with homogeneous data type. So in this case, you have a list of two numbers. So we pass it through the tensor constructor, and what you get is a tensor of dimension 1, okay? And there are two numbers in that dimension. As you can see, this creates a tensor, and now we have just one dimension of this tensor, and within that dimension, there are two numbers. Okay, so this is dim, and of course, if you check the shape, okay, gives you that, tells you that there are two numbers in the first dimension. So since this is an online class, there's no way to, if you have any question, you can always, for those of you who are physically in the classroom, you can send the message to the moderator. He has a way of sending it to me. And for those online, I will be following your comments live on the YouTube channel. Okay. Remember, like I said, you can create multi-dimensional tensor. In this case, we are creating a tensor, okay, of 2 dimensions, which essentially is a matrix. So how did I know about the dimensions? If you count the number of open brackets, there are 2 in this case, and on each dimension, okay, there are 2 items. So on the first dimension, there are 2 items, and also the second dimension, there are 2 items. This gives you a 2 by 2 matrix. Okay, we can check the dimension. We can also check the shape. Okay, on the first dimension, there are 2 items, and also on the second dimension, there are 2 items. Similarly, you can create a 3D tensor, the same arguments. Okay, the dimension of the 3D sensor is 3, and the shape is that there is 1 item in the first dimension, 3 items in the second dimension, and 3 items in the fourth, 1 in the 0 dimension, sorry, 3 in the 1st dimension, and 3 also in the second dimension. So you count the dimension from, the dimensions are actually indexed from 0, 1, 2, and 3. Okay. So this is a graphical illustration of what I'm trying to explain. Okay. So you count the number of dimensions by the number of open brackets in the list or in the tensor. In this case, there are 1, 2, 3. So there are 3 dimensions. The first dimension is indexed at 0. The second dimension is indexed at 1. And the third dimension is indexed at 2. Okay. At dimension 0, there are 3. There's just 1 item. Okay. At dimension 1, there are 3 items. And at dimension 2, there are also 3 items. So that gives you a shape of 1 by 3 by 3. One by 3 by 3. Okay. One by 3 by. All right. So we've seen how to make a tensor. So let's summarize what we see here. Okay. A scalar value is a single number. Okay. The number of dimensions in the scalar value is 0. Okay. For a vector, okay, there is just 1 dimension. Okay. And for a matrix, there are 2 dimensions. For an n-dimensional array, there will be, can be any number, a being the 0. A is a 0-dimension tensor, is a default scalar. 1 is a 1-dimension set, and then 2 is a vector. Okay. All right. So this is a big pictorial view of all the things that we've been talking about. All right. So you might be interested in making a random tensor, like a tensor with a random value. How do you do that? Okay. Now, typically, the PyTorch library gives you a way of doing that, where the function is called rand, all right? And then you specify the shape of the tensor. So this means that I want a random tensor with shape 3 by 4. Okay. Now, so the first line creates a random tensor. Okay. And then the second line prints out the tensor. Okay. And the type of the tensor. Okay. So the tensor itself is this number here. Okay. If you notice, the number of dimensions in this tensor is 2. Okay. And then the values, these are the random values that were generated as a result of this command. So I have 3 rows. In this case, you can think of it as 3 rows. Okay. And on the first dimension, there are 4 values. Okay. 1, 2, 3, 4. So that makes it 3 by 4. Okay. And as you can see, the data type for the elements in this random tensor is a float. Okay, so this is a way of creating a random tensor in PyTorch. So all you need to do is specify the size of the tensor, the shape of the tensor, which invariably means it's the size, and then you get a randomly generated tensor. Okay, this is another example where we create a 3-dimensional tensor. Okay, where we say the first dimension should have 224. Okay, the second dimension should also have 224, and the third dimension should have 3 elements. This actually, when you look at it, corresponds to an image, a colored image. Okay, so if you visualize this maybe with a matplotlib, what you get is an image, some random image with random noise. Okay, so the next line prints the shape of the tensor. Okay, and the number of dimensions of the tensor. So of course, what we hope to get would be 224 by 224 by 3, and the dimension of the tensor would be 3 because there are 3 dimensions in this tensor. And that's what you see here. Okay. All right. So let's continue. You may also be interested in making a tensor with either 0 values or 1s. Okay. What you need to do is you get a hold of the torch library, and then you call the zeros function. I think this is actually a static method within the torch library. So you call the zeros function, and then you pass in it the shape of that tensor. Okay, so in this case, what I have, just a moment. Oh, okay, the size of the screen. Sorry about that. All right. Okay, so I hope the size of the screen is much better now. Okay. All right. Okay, so you might be interested in making a tensor of whose values are all zeros. Okay, and the shape of that tensor should be 3 by 4. Okay. All right. And yeah, so this creates a tensor of size 3 by 4. Okay. And we can actually view the tensor and the data type of that tensor. By default, most tensor will assume a data type of floats with the 32-bit floating value. So this is how you create a tensor of size, of a tensor of zeros. You might also be interested in creating a tensor of ones. It's still the same idea. You grab the torch library, and then you call the static I want to believe this is a static method, but let's just say you call the method or the function once, passing as a parameter the shape or the shape of that sensor. Okay, tensor. So this means that you would have on the first dimension you have 3 items, and on the second dimension you have a maximum of 4 items. Okay, so as a recap, this creates a tensor whose values are all zeros, and this creates a tensor whose values are all ones. Okay, the function, the way you do either of the two is similar. You call zeros in the case of creating a zero tensor, and you call ones in the case of creating ones tensor. Okay. You may also be interested in creating a range of tensor, as in a tensor whose value ranges from a particular number to a particular number. Okay. Now, to do that, you use the arrange function, specify the start of the number, and you specify the end of the number. If you're interested, you could also specify the step. Okay. So, for example, if I specify 0 as the start, 10 as the end, and with the step of 1, it means I'll have tensors from 0 all the way to 9. Okay. All right. So this is how you do it in NumPy. Now, if you run this on your computer, you would notice that it says that the first way of doing it is deprecated. So what that means is that this very function will not be supported in the coming release of PyTorch. So to be on the safe side, you might want to use arrange, okay, instead of range, okay. Otherwise, maybe in the future, your code might break if you're using this way of making a sequence of tensor. So like in this case, I have arrange. I want values from 0 all the way to, and I want to end at 10 with a step size of 1, which means I will get values from 0 all the way to 9. The last value is not included. So it is usually n, the last item is usually n minus 1. Okay, so let's do a little bit of modification here. Let's say we take a step of 2, then it means I will have values from 2, 0, 2, and 4. The difference will be 2. So 2, 0, 2, 4, 6, and 8. 10 is not inclusive. Okay. You might also be interested in making a tensor with the shape of another tensor. For example, you can say you want to make a tensor, a zeros tensor, like another tensor. Okay. For example, if you look at this 0 tensor, okay, this has a shape of it has 1 dimension and a shape of 1, 2, 3, 4, 5 items. Okay, so if I run this code, it means I'm going to have a zeros tensor whose shape is the same as this input here, meaning I'm going to have a zeros tensor with how many items here? 1, 2, 3, 4, 5. 5 items inside. Okay. All right. So that's that about making a tensor like another tensor. Now within the PyTorch framework, there are different data types. Okay. Some are specific to CPU, and some are better for GPUs. Okay. So what do we mean by that? You remember in the introductory class we discussed. No. A tensor, think of a tensor as a classical array. Okay, so it cannot take different type. Okay, however, you can make a list of tensors, so where each of the elements of that tensor can be of different type, but the tensor itself cannot take different types. Okay. All right. So so like I said, there are different data types in the okay. There are different data types you'll find with the PyTorch implementation. Some are more suited for your GPU, and some are also more suited for CPU. Typically, the most common and default type is either float 32 or just float. Okay, this means that this is referred to as 32-bit floating point integer. Now, there's also other representation for float. For example, you can have 16-bit precision floating point. You can or half. You can also have 64-bit floating point. For those of you who are into scientific programming, this will be very, very helpful, especially if you don't want to run out of memory and if you have very large arrays and large numbers. Okay. There are also integers. Okay. Yeah. So you can follow this link to get more information on the list of other available tensors. So this is let's see how to create some tensors with specific data type. Okay. We can do so using the data type parameter. For example, if you look at all the implementation, all the code we've been running, we didn't specify the data type of the tensor. So by default, it took the float and 32 data type. So, but we can be specific. Okay. In this case, here we are creating a tensor. All right. Now we specify that the data type is none. Like I said, by default, it will assume that it is a 32-bit tensor. We can also decide where the tensor should reside. Recall we talked about the processing unit you have in your computer being the CPU and the GPU. So if you specify that you want your tensor to live in the CPU, then of course you might as well not even pass any argument for this parameter. So by default, it's going to reside in the CPU. But then again, you can specify that your tensor should reside in the GPU, in which case you specify the GPU ID. Okay. Now, in the course of building deep learning models, okay, some of you can see my screen. All right, so let's see. Just give me a moment. Let me reshare. Okay. So let's assume I want to believe everybody can see the screen now. Okay. This moment. All right. So I don't know. Can you all see my screen? Okay. Okay. All right. Okay. So here we created a tensor, okay, of this shape. We wanted to assume the default floating representation data type, we wanted to assume the default representation, which in this case is your CPU. Okay, and very importantly, this variable. Okay, so this means that you want the gradient for this tensor to be calculated during something called backpropagation. Okay, if you set this to false, as it is right now, it means that the gradients will not be collected for any operation that involves this tensor. Okay. All right. So here we specifically make another tensor, but this time we are saying that this tensor should be of float 32. Okay. All right. So we've talked about a lot at this point. So let's now see how we can get more information from our tensor. Okay. So yeah, we can, get the shape, the type, okay, and also the device class. For example, if our tensor lives in the CPU, we would know, okay, and if our tensor also live in the GPU, we would know. Now, if you look at this, we're creating a random tensor. Its shape is 3 by 4. Okay, we want to print out the shape. Okay, print out the type of the tensor, and also where the tensor live, whether CPU or GPU. So if I run this code, what I see is this is the random tensor that I just created. Okay, the shape is 3 by 4, which is also specified here in my code, and it lives in my CPU. Now, this is very important because if you want to perform any mathematical operation on a tensor, all tensors must be in the same device. Okay, so you cannot add a tensor that lives in the GPU with a tensor that lives in the CPU. There are two different memory locations, and that won't work. Okay, so if you want to add two tensors, they both have to be, you want to do any mathematical operation on a tensor, they both have to be in the same memory location, whether CPU or GPU. All right, so this is where we come to the cool part, where we can manipulate the tensors. Okay, and this is also very, very, very important in building some of these models that we'll be using. Now, you can perform all the basic arithmetic operation you already know. We can do addition, we can subtract tensors, we can multiply tensors, and interestingly, we can do division on tensors. Okay, now the division in this case would be a division by a multidimensional tensor and a scalar value, because division will involve element-wise division. We'll see that in a moment. We can also do multiplication of tensors. So let's start. Okay. Now, suppose you have a tensor. Now, this tensor is one-dimensional. The shape is just 3, because there are 3 elements here. We can simply do some matrix and scalar addition or multiplication. In this case, I have a tensor and I add 10. Okay. Now, this is a multidimensional tensor. This is the scalar value. Okay. Now, it doesn't really matter if this is not really of a type tensor data type, because there is an implicit casting that goes on once you do this addition or any of these mathematical operation. So now we add 10 to this, which means we are adding 10 to every element in this tensor. This is what we call the element-wise addition. Okay, so if I add 10 to this tensor, what I get is 11, 12, and 13. And that's what you see here. In the same way, I can multiply this tensor. Okay, so this is a multidimensional tensor with a scalar multiplication, much like your typical vector operations, in mathematics, where you can, um, um, yeah, you can think of it as a vector space for those of you who are more mathematically inclined. All right, so a vector space operation anyway. So we can add multiply 10 to this tensor, which would do element-wise multiplication. So this would be 10 times 1, comma 10 times 2, and 10 times 3. So the output becomes 10, 20, and 30.
Hey, boss.
Okay.
I'm good. I'm good.
Good job.
All right. So we can retrieve.
And then you left.
So, well, we can simply just print out the tensor and you get the values located in this tensor. But if you notice, the values didn't change. That's because we did not assign it. We did not replace the content of that memory. We just multiplied. Okay, in this case, we just added. All right. If we want the value to change, then we can say tensor equals to tensor times 10, which means the result should also be assigned back to the tensor variable. Okay. All right. So, yeah, we can also add and subtract. In this case, we are taking out 10 from every element of the tensor, but then we are replacing the result with the tensor variable. So in this case, we are modifying the tensor itself. All right. So initially the tensor was 1, 2, 3. By the time you subtract 10 from it, you have -9, -8, and -7. We can also do the same with addition. Okay, we have just changed it to -9, -8, -7. We can take it back by adding 10. Okay, giving me 1, 2, and 3. You can also do element-wise multiplication. Now, this is very important because this multiplication function in the Torch library does element-wise multiplication. Okay, the same thing we did somewhere here. Okay, so I can use the Torch library to do element-wise multiplication. In this case, torch.multiply, and I pass in tensor and I pass in the scalar value. Okay, but of course, this did not change because I did not replace the value of the tensor with the value of the modification with the previous on the previous variable. So it is not so common to use this function because, I mean, it involves probably writing too much. You can just use the simple multiplication operator instead of the more. Okay, like in this case, yeah, good. You can use the multiplication operator just like we did here, okay, to achieve the same result. All right. If you also want to do element-wise multiplication, then of course you can use the mul function, or you can just simply just put the use the multiplication operator. Now this is element-wise. Okay, it's different from doing a dot product between two vectors. So let's see an example. So we print the first tensor and the second tensor. All right. But in between, we put a star just to give you visual representation. That is essentially what is printed here. Now, if you now print both tensors, tensor times tensor, this means we want to do element-wise multiplication, meaning what you have here is the resulting variable will be a tensor, okay? But the value of that variable will contain element-wise multiplication of the two other tensors. So in this case, I have 1 times 1, which is 1, 2 times 2, which is 4, and 3 times 3, which is 9. Okay. Now, this kind of operation is not so common. Okay, element-wise multiplication. All right, but what is common is the actual matrix vector multiplication and matrix multiplication, which defines typical linear transformation in mathematics. And if you recall in our introduction to neural networks, we said that these neural networks are function compositions, okay, where you multiply a matrix with a vector. So these are the kind of things that we'll be doing, okay? So to do that, you can simply just think of a one layer network as a matrix and a vector multiplication, and then you pass the result through a nonlinear function, or a nonlinear function, which is essentially an element-wise operation on the result of the matrix vector multiplication. So how do you do matrix multiplication? All right, you use the matmul function. Notice that this is different from the mul function. The mul function does element-wise. The matmul function does matrix vector, matrix multiplication. Another way to do it is to use this operator, the @ sign. Okay, but very importantly, just like if you recall back in your elementary linear algebra class, the multiplication has to be well defined. For example, you cannot multiply a matrix or a tensor of shape 3 by 2 with another tensor of shape 3 by 2. This will not work. Okay, this kind of composition does not work. All right, for it to work, then it means that the last dimension of the first tensor must be exactly the same thing as the first dimension of the second tensor. Okay, so this would work because on the first tensor we have a shape of 2 by 3, and on the second tensor we have the shape of 3 by 2. Okay, now if you notice, this is the last dimension, the shape of the last dimension of the first tensor, the shape of the first dimension or the 0 dimension of the second tensor, and they both match. This is 3 by 3. The resultant multiplication will give you a 2 by 2 matrix. Okay, this would also work because there is 2 in the last dimension of the first tensor, and there's also 2 in the 0 dimension or the first dimension, depending on how you want to count it, of the second then tensor. So together you get the output will give you a 3 by 3 tensor because you cancel out the dimension that match. So this is what I'm trying to say here. The result of this gives you a 2 by 2. The result of this gives you a 3 by 3. So as a short exercise, maybe you can do it for those of you who are online or maybe on a piece of paper. I'll just type in a simple classwork to give you an idea. So let's put this one in. Let's just put this in Markdown. Let's say you have, okay. All right. So for those of you who are watching, also those who are live in class, if we have maybe 3 by 4, okay, multiply by multiply by maybe 3 by 5, okay. Now with this tensor, would this multiplication work? Okay, think about it. What if we have, let's say, shape 5 by 2, 3, and shape 3 by 5 or 3 by 10. Okay, will this multiplication work? And if it does, what is the shape? So try that, and let's even go more complicated. Let's say you have a tensor of shape 2 by 1 by 4 by 3, okay? And you multiply this with a tensor of 5 by 2 by 1 by, oh, sorry. Let's say 1 by 2 by, let's just say 8. Will this multiplication work? And what will be the resultant tensor at the end of that multiplication? So the take home here is that the @ sign is the operator in terms of matrix vector multiplication or matrix matrix multiplication, or tensor tensor multiplication, you put it that way. So let's look at a few examples. Now we import a tensor, okay, and then we make a tensor of size. There's a one-dimensional tensor. There are 3 elements in this tensor, and those values are 1, 2, 3. Okay, so there's 1D tensor. In that dimension, there are 3 elements. So let's look at some multiplication. Remember, if you use the standard star, what you'll be doing is element-wise multiplication. So in this case, this tensor has 1, 2, 3. So if I do element-wise multiplication, I'll have 1 times 1, 2 times 2, 3 times 3. Okay, giving me 1, 4, 9. All right. If I do use the function matmul, okay, this is not an element-wise multiplication. Think of it as multiplying 2 matrices together or 2 vectors together. And this, in the case of a vector, that would be the dot product of the vector. It's like saying you would have this tensor, okay, this tensor transpose this tensor, okay? Is this clear? So the dot product of these two will be 1 times 1 plus 2 times 2 plus 3 times 3. The value is 14. Okay. You can also do that. Remember, I said instead of doing matmul as a function, you can also use the @ sign. Okay. These two operations are the same. So in this case, we are doing the dot product of these two tensors. In this case, we are doing element-wise multiplication of the two tensors. So this gives me the same result as 14. Now you can do matrix multiplication by hand, but obviously it's not advisable. Okay. You can also do matrix multiplication by writing a loop. It's also not advisable. Well, dot product, either dot products or either element-wise operation or dot product form using a simple loop, but it's not really advisable. This is because there are inbuilt operations in these libraries that does these kind of operations in parallel. So it's a lot faster to do it, using the approach provided by the library and doing it by writing simple loop. So this is an example of such operation. So here we take the time of this cell. We just write a simple loop. In this case, we do simple dot product where we multiply the corresponding element and we add them up. And that gives me a value of the same value that I'm looking for. Okay. But it does it at the time it took to run this operation is 2.53. This just means that we want to benchmark this operation. But if we do it with the operation provided by the Torch library, like I said, these are extremely parallel operations that can be done implicitly for us. If we also do the benchmark for the operation using the Torch library, you can see that it's a lot faster. This is accomplished in 990 nanoseconds, okay? But this one took 2.53 microseconds. So imagine if you have a lot of matrix multiplication. Okay, so let me explain that. So in this cell, this is basically saying I should record. This is basically saying that I should record the time it takes to run the cell. Okay, and like I said, we can either do either of these operations, manually, like I said, but not really manually, like just by writing a simple loop. In this case, we wrote a simple loop to do the dot product. We started with a value of 0. We iterate. We created in the indices for the elements of the tensor, in which case those indices will run from 0 all the way to the length of the tensor minus 1. And within that loop, we do we multiply the element wise, and then we add the value resulting to the dot product of those two tensors. If you run this, like I said, in this case, it took 1.26 microseconds to execute this cell. Okay, but if you look at doing the same thing using the function provided by Torch library, okay, the same thing. I mean, we did it less than 0 nanoseconds. Okay, so that would be divided by 10 order of magnitude faster than 0, compared to 1.2 second. Like I said, this is also equivalent to doing, just a moment, let me make it here. This is also equivalent to doing something like this. So our tensor is tensor. I can do at tensor. Okay. And I can also decide to benchmark this. Okay. All right. So let's see what I got. The same thing. Okay. So you can either use the mathmal function or the at, but it's a lot faster because this operation is done in parallel. Okay. If you recall the manipulation of the shapes that we talked about, okay, if you have not done this exercise, maybe what we are going to see now will give you an idea of the result and of the exercise. Okay, now this is also very important because when you are debugging, if you create a model, if you design your model from scratch, you do all the composition with the matrices and all that, it involves, like I said, matrix multiplication. So those operations must be well defined, like the shapes of the matrices must be well defined. And this is really, really important, no matter the kind of architecture you're using, because most of the errors you are going to get will involve shapes. So you need to understand these shapes. Let's take, for example, let's say I make tensor A, and this tensor is two-dimensional tensor, okay? The first dimension contains 3 elements, the second dimension contains 2 elements. So giving me a 3x2 tensor. And I do the same thing. This is also a 3x2 tensor. So this is tensor A and this is tensor B. If I do mathmal between these two tensors, I'll definitely get an error. That's because there is a shape mismatch between these two tensors. Okay, so this is what we're saying. I get an error, and you also need to be comfortable with these errors. Now it says here that there's a runtime error in doing this multiplication. Matrix 1 and matrix 2 shape cannot be multiplied because one is 3x2, the other one is 3x2. Remember the golden rule: the dimensions of the dimension of the shape of the last dimension must correspond to the shape of the first dimension. Okay, here the shape here is 2, here the shape here is 3. They don't correspond, and this is the reason why this operation failed. Okay, now I can decide to solve this problem. It depends on the kind of application. Okay, I can decide to solve the problem by first taking the transpose of the first one. So that would be dot T. Okay, which means I make all the rows the columns and all the columns the rows. Essentially, this will give me a 2x3 matrix. If I do that, then what I'm going to get is a 2x3 matrix multiplied by a 3x2, and the dimensions will correspond, and I shouldn't have any problem. Okay, remember in this case, I just swap the dimension, okay, so as to make this multiplication well defined. But as it was, I have a 3 by 3 matrix and a 3 by 3 matrix. Obviously, I'll get this issue. Okay, and this is what we just discussed here. Okay, so one way, like I said, is to take a transpose, but you have to be sure of what you're doing. Okay, matrix multiplication, think of it as function composition. Okay, meaning you're taking a map from one vector space to another vector space. So the dimension of your range must correspond to the application with which you want to do that, which you want to use to solve the problem. So if your range is not well defined based on the problem you're trying to solve, then doing a simple matrix transpose before multiplication would not really make sense. So it's either you change the shape in the way you want it so as to match the kind of problem you want to solve. I don't know if that makes sense, but yeah. Give me a moment. I need to take a break, a call. Hello, can you hear me? Hello, if you can hear me, I guess you can. Okay, so we continue. All right, so like I said, one way to solve the problem is either to take the transpose of one of the matrices so as to make the multiplication well defined. Okay. All right, so this is essentially what we just did here. So if you print these two matrices, this gives you the values. And then remember, this is a 3 by 2 matrix and a 3 by 2 matrix. So you can either transpose the first matrix or you transpose the second matrix. All right. Okay. So yeah, so the operations work when the operation can either work when B is transposed, also when A is transposed. Remember, like I said, that the basic essence of this is that the multiplication must be well defined for it to work. So in this case, we took the transpose of B, okay? And if you take the transpose of B, so let's work it out quickly. You have 3 by 2 matrix times 3 by 2 matrix. In this case, if I take the transpose of B, I would get 2 by 3 matrix, and the output will be a 3 by 3. Okay. But if I have 3 by 2 and I decide to, so the output here would be a 3 by 3. Okay. But if I decide to take the transpose of the first one, 2 by 3, okay, and I multiply this with a 3 by 2, what I get, okay, the dimensions that match will cancel out, giving me a 2 by 2. Okay. So this is why I said that it is very important you know exactly what you're trying to do and what you're trying to accomplish in these multiplications. You can also use the MM, which is matrix multiplication. It's a short form for MITMUL, to do the exact same thing. But most importantly, the dimensions must match. If you have the notebook, you can follow this this link to take you to these animations where you can simply see how the multiplications are done. Okay. All right. So that brings us to another very important part to discuss, which is a linear transformation. So matrix vector is a linear transformation. Essentially, projecting the vector from one linear space into another linear space. Okay. All right. And there is a mechanism within PyTorch that allows us to do this. All right. That mechanism is touch.nn.linear. In the background, what it's actually doing is it defines a matrix B, okay, A and a vector B, such that if you pass in another vector X, it essentially projects that vector to a different linear space. Okay, so whenever you use this function within PyTorch, this is essentially what you're doing. So this makes it a lot cleaner. So X is the input, A is the matrix, and B is the vector or the bias. But of course, we will need to specify the shape of this transformation. Okay, where we would say, okay, we want to have the number of features that comes in, which is essentially the shape of X, okay, and the number of features that should come out, or the number of dimension of the vector that should come out. Okay, so this is an example. So we start by setting a random seed, okay, and then we make a linear transformation, okay. So this is actually an instance of this definition here, linear transformation. So let's take this thing into pieces. This means that we are going to be having a matrix of dimension 6 by 2, because the number of features, okay, is 2, okay, and the number of output feature is 6. So this gives us a transformation with a matrix of 6 by 2. So let's see how it works. So I make this linear transformation, all right, and then I say my X is this tensor A. Let's see what tensor A is here. Okay. So tensor A is what's the dimension? Okay. So tensor A is of dimension 3 by 2. So what does this mean? It means my X is a matrix. Okay. If you work out the maths, it means I want to multiply the input, which is 3 by 2, okay, times another matrix. Now this matrix is going to be so this is number of features is 6. Okay. All right. And number of out features is 2. But if you take the transpose of this, what you get is 2 by 6. Okay, which is essentially this guy here, plus some bias that corresponds to whatever value, whatever dimension you have to for this range. And then that should give us a resultant matrix of 3 by 6. Okay, so working that out, okay, we define a linear map, okay, with this dimension, and then x in this case is our tensor of dimension 3 by 2. By the time we now pass x to this, okay, we can now inspect the shape of the resultant value. So here we are printing the shape of the x itself, and here we are printing the shape of the output from this linear transformation. And like we just resolved, the shape of x is 3 by 2. Okay, the shape of the output is 3 by 6. We worked it out just now. Okay. I don't know if there are any questions. If there are questions, you can make your comments on the you can make your comments online, and then I'll answer. Okay. All right. You can now. This is very important. So you have to on your own review this and get a better understanding. If you don't, you can always ask a question, maybe in the in whatever means or channel provided to do so. You can also find the minimum, the maximum, the mean, the sum, essentially aggregate statistics for tensors. All right, so let's look at this first declaration. So we declare a tensor, okay, that would have value from 0 all the way to 100, okay, but with a step size of 10. So essentially, these are the values, okay? So within this setup, I can find aggregate statistics for this tensor, okay? All right, so we can find the mean. Basically, now this is essentially an object of a tensor, okay? And within that, you have functions like mean, max, median, and all that. So I can do x.mean, x.max. I can also do x.type, and then change the type of the tensor, and then take the mean. Okay. So this is essentially what you have here. Okay. All right. Similarly, in this case, you can use the static method provided by the Torch library to calculate any of these summary statistics like mean, max, and the rest. Okay. Now, one thing that is also common is to do positional summary statistics. Remember, we are dealing with high dimensional tensors. So you might want to calculate the mean or the max or the median across a particular dimension. For example, let's look at this tensor. Okay. So we have tensors whose value ranges from 10 to 100 with a step size of 10. Okay. You can do the tensor.argmax, What does this argmax mean? Because you see this thing a lot in optimization. This means you are returning the index with the largest value. In fact, okay, I think everything is printed out at the bottom here. So if we print this tensor, the values are 10, 20, and all that. Okay. If you do the argmax of this tensor, what we are saying is we want to return the index with the largest value. In this case, the index with the largest value is 8. Okay, so if you count it, all right, it will be at 0, 1, 2, 3, 4, 5, 6, 7, 8. So the argument, the position with the largest value is 8. It is different from the maximum value of this tensor. The maximum value of this tensor is 90. The position where the maximum value is found is at index 8, which is what you see here. Similarly, the minimum value of this tensor is 10. The position where that is found is at index 0. So this is very, very important. If, for example, you're trained a model, maybe at the last layer, you have a softmax output, which essentially is a vector. And then you want to figure out the class, in the case of classification, with the most probable label, then you can do the argmax of that vector with the view that each of the index represents a particular class label. You can also change the tensor type. So here you have a tensor of floating points ranging from 10 to 100. The type is 32. You can change it. All right. So all you need to do is just do the tensor that type, and then you specify the new type. In this case, now we have changed it to a tensor of type for 16, floating point system. Yes, there's a homework at the end of this lecture material for you to practice. Okay. All right. So this is how you change the data type for the tensors. So there's an exercise here. So far we have covered a few tensor methods, but there is a bunch more in the tensor documentation. Okay. So I recommend spending 10 minutes scrolling through and then you look into any of the functions that catch your eye. All right. So another very important thing you do with these tensors is to reshape the tensor. Okay. So if you have a tensor of a particular shape, okay, you can change the shape of this tensor. All right. So these are the methods that I use to do that. So you can either shape the tensor, squeeze the tensor, that is reduce the dimension, or unsqueeze the tensor, that is expand the dimension. So what do these things mean? If you reshape, it means you're changing the shape of the tensor. Essentially, you're rearranging the elements of that tensor. Okay. So the reshape reshapes the input to the specified shape if it is compatible. Okay. And you can also do touch.tensor.shape. Okay. Tensor.view will return the original tensor in a different shape, but it will share the same memory. Okay. The same as the original data. Touch.stack will concatenate the tensors in a sequence based on a particular dimension. Okay, so essentially you're going to get a new number dimension if you stack up these tensors. You may also decide to remove certain dimension. For example, if you have a tensor of size 1 by 3 by 3, you can squeeze that tensor to 3 by 3, knocking out one dimension. Okay, similarly, you can also unsqueeze a dimension by expanding it. Okay, so if you have a 3 by 3 tensor, you can expand it to 3 by 3 by 1 or 1 by 3 by 3, depending on the direction of the dimension, the specific axis of the dimension you want to increase. Okay, so these are short exercises to explain the concept. So let's say you have a 1D tensor with values from 1 to 7. Okay, if you look at this is a 1D tensor. Okay, there are 7 values there. Now you can reshape this to 1 by 7. Very importantly, the new shape, the product of the dimension of the new shape must be exactly the same thing as the product of the dimension of the previous shape, because you don't expect to have additional values or add additional numbers in the new dimension. So like in this case, I have a tensor of 1D, okay, and there are 7 items. I can reshape this to 1 by 7. So if you take the product, it's still 7 items. Okay. So I now reshaped it to 1 by 7, and the dimension is now 1, but there are 2 items in the first dimension. This is now 1 by 7. You can also change the view with the touch.view. In this case, I have X. Okay, I can view it as 1 by 7, in which case I get the same result. Okay, so very importantly, if you do touch.view, okay, it creates a new view of the same tensor. All right, meaning if whatever happens to the tensor in the new view also happens to the original tensor. You can also change the dimension of a tensor by slicing it. In this case, if you look at this tensor, okay, I'm viewing it as 1 by 7. Okay, I can say that I want to slice it along the first axis. I want to take all the elements of the first axis, okay, and then set it to 5. Okay, essentially what that means is I'm setting the first element of the tensor to 5. In this case, now it was 1 before, now it has been changed to 5. And if you print the other tensor from which you derive this view from, the value has also been changed, to 5. So what this means is that this view command, okay, gives you a different view of the same tensor. So essentially, this is a reference to the previous tensor. So whatever happens to this new assignment also happens to the previous tensor. You can also decide to stack up tensors. Now, so let's see. X is a 1 tensor. It's how many items? 1, 2, 3, 4, 5, 6, 7. I can stack them up, okay, using touch.stack. All right. So I'm stacking X, 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 but along the 0th dimension. So this means that I'm going to have, so the 0th dimension will now increase from 1 item, okay, to 5 items. So you have now 4 items. Okay. So meaning on the 0th dimension, I now have a stack of each of these. So you expect 4 items on the 0th dimension. So that's essentially what this does. Okay. So as you can see now, I now have a tensor with shape 4 by 1, 2, 3, 4, 5, 6, 7. All right. You might also want to unsqueeze a dimension from a tensor. Like I said, on squeeze means you're removing a dimension from the tensor. Sorry, squeeze means you're removing the dimension. On squeeze means you're expanding or increasing the dimension. Okay. So let's look at this X shape. So here we print the previous value of the shape. We print the tensor and the shape. Now, after unsqueezing, we also do the same thing. So what do we have? This is the value of X reshaped. This is a 1 by, this is 1, 2, 3, 4, 5, 6, 1 by 7, which is this one here. Now we can knock out the, we can squeeze this dimension because 1 is really redundant. We can just say, okay, well, we want to only have a tensor with the 0th element having 4 items. Excuse me, let me plug my laptop. I think I'm running out of power. Okay. All right. So by squeezing this, I now have a size 7 as opposed to 1 by 7. Because if you take the area of the element or the number of elements in this is still 7. 1 times 7 is 7. 7 is 7. So this squeeze operation is well defined. Okay. We can also unsqueeze. Like in this case, so I have the squeezed version, which is just shape 1D tensor of shape 7. Now I can unsqueeze it by adding 1 dimension, which means I want to expand it. In this case, I add the dimension along the 0th dimension. So it means 1 is going to be 1 by 7. All right. If I say the dimension should be 1, it means I'm going to have 7 by 1. Okay. All right. So this is 1 by 7 because I'm unsqueezing it, at the 0th dimension. So let's try it for dimension 1. Okay. So this is now 7 by 1 because I'm squeezing it from the right. I'm squeezing it from the right. Okay. Okay. All right. So we can also rearrange the order of the axes, meaning you can permutate the shape of the tensor. If you look at this tensor, you have 224 by 224 by 3. Okay. You can decide to rearrange the shape of this tensor. That's what the permute does. So I can rearrange it to 234 by 3 by 224 or 3 by 224 by 224. Now this is important because if you are visualizing this, you can think of this as an image, okay, with 3 channels. If you're visualizing this, some image library will require the channel dimension to come first and the dimension of the width and the height of the image. Okay. Similarly, if you're doing, we are building these neural networks, some of these libraries require the channels to come first before the shape of the tensor, and vice versa. So it depends on exactly what you're trying to do. So let's try to understand what this does. This permutate or permute is saying the shape of the second index. This is the second index 3. Okay, should now be in the first index because 2 is actually in the first its 0th index. The shape of the 0th index should be in the second. Okay, and the shape of the first index should be in the 3rd. So what does this imply? It means it will now be 3 by 2 44 by 244. Okay, so let me say that again. This is our input. All right, I want to rearrange or permute the shape. Okay, I would say, okay, well, the index at 2 should come first. Okay. The index as 3 should follow. So index at 0 should follow, and the index at 1 should be last. Okay. So this way I have 3 by 224 by 224. Suppose I want this 3 to be in the middle. I would say that 3 should be in the middle. So that's index 2 should be in the middle. So 2 will be here. Okay. Index 0 should remain the way it is. Okay. And index 1 should be the last. So this means I'm going to have 224 by 3 by 224. Okay. And here it is 224 by 3 by 224. Okay. All right. So that's about permuting the tensor. Okay. You can also select or slice tensors. Okay. Now in this case, I have 10 tensors. Oh, what? 9 tensors actually. Okay. That I've reshaped to 1 by 3 by 3. Okay. Now I can, perform some, indexing of the tensor. For example, I can say, okay, I want to access index at location 0. Okay. What does that mean? It means it will give me everything inside this location. Okay. I can say I want to access index at location 0, which is everything inside this 0th index, but I also want to access the first index of that, which is essentially this element here. Okay. All right. I can also say, okay, I want the first, the 0th index and the 0th index of that other index and the 0th index of that index, which will give me 1. Okay. So this is how, what did I do here? Okay. So we have, all right, let's see this. Okay. So let's see. So 0 at 0 at 0. Okay, let me just take it out of this function bracket. Okay. Okay, let's see. All right, so in the first bracket, I have everything here. Okay, in the second bracket, like I said, I have, this is the first bracket, okay, which gives me this matrix. Okay, but within the first matrix, which is this guy, I want to get the 0th index, which is essentially this here. Okay. Now, within this one, I want to get the 0th index in that one, which is essentially 1. Okay. All right. So you can also do the same thing. You can slice along the dimensions. So here, I would say, okay, well, I want to get in the first dimension, all the items in the first dimension. I want to slice along the first dimension. I want to get the 0th index, which gives me this content here. Okay. I want to slice along the 0th dimension, the first dimension, and I want to get the first value is, well, the second value in that dimension, and that's that. Okay. So this is, all right. I think we are almost rounding up. Let's see how much we have left. Oh, okay. All right. I think we have to move a little bit faster. Now, you can manipulate between tensors and NumPy. That is, you can convert from tensors to NumPy. Okay. So what you see here is we have a NumPy array, and then we make it a tensor. And that's essentially what it is here. Okay. But if you notice, they represent different memory locations. So here we added one to the array we created, but the other tensor remain the same. This is what we're just showing here. Okay. We can also take a tensor to a NumPy array. So here we make a tensor once, and we took that to a NumPy array, and then we can print them. Okay. And similarly, they represent different memory location. Okay. So if I add one to the tensor, it doesn't imply that the NumPy array will change. So usually when you're making this when you're doing this deep learning project, you want to have to be able to reproduce the results at any time. So that's reproducibility, where you set a random seed essentially. Okay. So let's say we make this tensor. Okay. We want to be able to have this result replicated. Then we can, specify a random seed. So each time we run this project or this program, the same random numbers come up, and that way we can easily use it to test the performance of our program. We talked about GPUs. Usually GPUs make your work faster. You can do all your operations within a GPU. Okay. Where you either move from CPU to GPU or GPU to CPU, but most times you do most of your work in GPU. That is, if you have a GPU. If you don't, you can easily get one from Colab. Okay. There's also some available from this cloud provider, for example, AWS, Google, and Azure. You can always get provision. If you want to know if you have GPU located, okay, within your system, especially NVIDIA GPU, you can run this command. I don't have in my system, so obviously it is not supported. Okay, so you either do this or on the command line. Okay, you do NVIDIA SMI. If you have GPU enabled, you should be able to see the GPU within your system. But like I said, I don't have, so it's not showing. So for those of you who are using your laptop, you can simply try this. Then you can either run this here, or you can run this in the command line. So in this example, this is a situation where the person actually, if you have a GPU, this is what you will see. Okay, especially NVIDIA GPU. Okay, to give you the version, the type of GPU you have, and also the memory. Okay, so this is, in this case, this is about 16 gig memory of GPU. Okay, which is fairly enough for running your project. And if you have any program running under this GPU, you see them here. Okay, so I don't have a GPU in my laptop currently, so this will be false. So you can also check within the PyTorch framework if you have GPU. So that will be torch.cuda.isAvailable GPU. Okay, so usually when you're programming, you want to switch between GPU and CPU if it is available. You can use this line of code. Okay, you just say, okay, well, my device, my default device should be GPU if it is available, but if it is not, it should be CPU. So when you're now creating tensors, you can specify the device that the tensor should use. Okay, you can also, if you have GPUs, you can also get the number of device count in that GPU. Like I said, I don't have one, so my device count is 0. Okay. If you're using an Apple machine, in order to run Python on Apple's GPU, you can use the touch.backend on MPS module. Okay, and be sure that the version of the Mac OS and Python is updated. So this is not a MacBook, so I don't expect that to be true. Okay, so at this point, I think we run out of time, but the rest of the material is fairly detailed in each of the cells. And yeah, I think we can just go through because we're almost there. Okay. So generally, you can do a quick setup where you can specify if you run this code on any laptop. Okay. All right. If you have it, if you are using a MacBook and there's a GPU, it will set the device to MPS. If you are using a non-MacBook and you have an NVIDIA GPU, it will set the device to CUDA. Otherwise, it will set it to CPU. So for most of your project, you might just copy this code and use it to select whichever GPU you have. To put a tensor on a GPU, all you just need to do is just specify to device. Okay. For example, this is a tensor, which by default lives in a CPU. You can move it to device, essentially. But I don't have GPU in my system, so the device is not defined. Okay, so this will be here. And by default, my device is CPU. Even if I move it, it doesn't change anything. It's still CPU. You can also move it back. Okay. If you have a tensor on GPU, you can just take it to NumPy array, which resides in the CPU. So at the end of this notebook, there are some exercises for you all to look at, just to get a good understanding of what we have been doing so far. So thank you very much. If there are any questions, please send it to the appropriate channel, and I'll do my best to answer. Have a good day.